This is exercise 5.3, Q2. I'm going to do some of the even numbered problems since the odd numbered problems are required for homework. For 5.3, we add one more rule. It's the conditional introduction rule. So remember, there'll be an introduction elimination rule for each of the operators. Last two exercises we did these. Well, 5.1 was these four. Then 5.2 added this one. Now we're adding this one. And the conditional introduction rule is a little tricky and a little different from the previous rules. And you can even see that just looking at it here. This rule is called, or uses what's called a subderivation, right? It's a sort of derivation within a derivation. And the idea here is, for conditional introduction, you're trying to prove a conditional or derive a conditional. If P, then Q. Now the way you derive a conditional is assume P is true and see if you can then derive Q. That's why this line here, it's going to be indented, and then there's going to be this vertical line to separate it from the rest of the derivation, because it's based on an assumption. You're making an assumption P and then trying to get Q. If you assume P and get Q, you have thereby proven that if P, then Q. Okay? So it's kind of a strange thing, but that's only because we're deriving a conditional, which is conditional. It's conditional on the antecedent, right? The consequent is conditional on the antecedent. So if we assume P and thereafter derive Q, we thereby prove if P, then Q. But the thing is, we don't know P is true. We're assuming it. And that's why it has to be set off from the rest of the derivation. Because all this other stuff in the derivation is assumed to be true, right? This is given as true, these premises. But this isn't true. It's just an assumption we're making to see if we can get Q, right? So if we assume P, get Q, we have thereby derived if P, then Q. All right. So when your conclusion, like in number 2 here, our conclusion here is a conditional, right? The main operator is a conditional. So whenever you're trying to derive a conditional, you can use conditional introduction. When you do conditional introduction, you always assume the antecedent of the conditional you want to derive. So we'll indent, we'll put that vertical line, and we'll assume F. And then we want Y and H. Okay? So we assume the antecedent of the conditional we're trying to derive, and we want the consequent. Now this is just like a note to ourselves here. Nothing in here has been proven or anything like that. It's just to remind us that what we want to get to. And when we get to Y and H, our conditional proof, or our subderivation for this will be done. Now we have to stay indented now because we're using this assumption. And again, we don't know it's true. So we're going to set it off from the rest of the derivation. It's kind of like when somebody gets sick, they quarantine them to try not to get everyone else sick. Well, we quarantine this assumption because we don't know if it's true. Remember, the whole point of a derivation is to go from true stuff to true stuff and end up with a conclusion that we know is true. So since we don't know if it's true, we indent and quarantine it. But we can use it now. So we have F conditional Y, so we can get Y there by conditional elimination of 1 and 3. So notice we use this assumption just like we would a regular premise or whatever. Okay? But it still stays off to the side just because it's not proven. Now we have Y, we can get H also by conditional elimination, this time 2 and 4. So line 2 is a conditional, line 4 is the antecedent, so that gives us the consequent. Now we can put those together, Y and H, because that's what we want to get. Conjunction introduction of 4 and 5. So line 4 and line 5, put them together in a conjunction. And again, that Y and H, that's what we wanted. So that finishes our subderivation. We come back to this original, this is called the scope line. Come back to this original scope line and we write our conclusion. And we get that by conditional introduction 3 through 6. Okay. Notice 3-6 because it's all this whole piece that proved. All right. So it's all of this. This is called the subderivation, all the indented part, and all of that is what proved to us that if f, then y and h. Okay. And again, this line now, this conditional has been proven. That's why we come back to the original scope line, right? This stuff was all indented. It was all based on this assumption f that we didn't know is true. But this now is true. We know it's true. And again, if you think about it, how do we know it's true? Because we assumed f and we derived y and h. So that proves then that if f is true, then y and h is also true. So it proves this conditional, if f, then y and h. Okay, number 4. Again, our conclusion is a conditional, so we're going to indent, put that vertical line, assume the antecedent that we're trying to derive, and want the consequent. Again, this want C is just like a note to ourselves to tell us, what we need to get to finish this subderivation. Okay, so now that we have S, we can get P by conditional elimination, 1 and 4. And now that we have P, we can get N by conditional elimination of 2 and 5. And now that we have N, we can get C by conditional elimination of 3 and 6. And C is what we wanted, so that ends our subderivation. Come back to our original scope line, S conditional C by conditional introduction 4-7. Okay. So again, we assume S, that's the antecedent of the conditional we're trying to derive. We go until we get C. All of this is indented. All of this is based on an assumption. But once we get C, we have proven that if S is true, then C is true too. So if S, then C. And again, since it's the whole subderivation that proves it, we have to do 4-7 as opposed to 4-7. Because it's not just line 4 and line 7, it's all of these. Okay, so number 6, again, same thing. Our conclusion is a conditional, so we use conditional introduction. We'll indent, vertical line, assume the antecedent of the conditional we're trying to derive, and want the consequent. Now we can get O by itself by conjunction elimination of 3. We can get C by itself, same way. Oops. Conjunction elimination of 3. So remember, that's the one that says if you have a conjunction, you can get each conjunct by itself. Now we can do these two conditional eliminations. So we can get H by conditional elimination 1-4. So line 1 is a conditional, line 4 is the antecedent, so that gives us the consequent. Then we can do the other one to get N. Conditional elimination 2-5. And now we put those together, H and N. And that's conjunction introduction of 6 and 7. And we're done with the subderivation because we wanted H and N, and that's what we got. So we come back over to this line, O and C, then H and N. And that's by conditional introduction of lines 3 through 8. So again, we assumed O and C, we derived H and N. That proves that if O and C, then H and N. All right. So again, notice the structure here is always the same. Assume the antecedent, derive the consequent, gives you the conditional. So the first line of the subderivation should always be the antecedent of the conditional that you're proving. And the last line of the subderivation should always be the consequent of the conditional you're proving. Okay. Okay, so 4, we got, again, a conditional as our conclusion, so we'll indent, vertical line, L, want, Q. So again, we assume the antecedent, and we go until we get the consequent here. So now with L, we can get not P by conditional elimination of 3, 4. If not P, we can get Q or R by disjunction elimination of 2 and 5. Now we can simplify, or we can get not R by itself by conjunction elimination of 1. And that allows us to get Q by itself by disjunction elimination of 6 and 7. So Q is what we wanted, so we assumed L, got Q, come back over here, L conditional Q by conjunction introduction of 4 through 8. So again, first line of our subderivation, L, that's the antecedent of the conditional we derive. Last line is Q, that's the consequent. Okay, one more. Now this one, notice we don't have a conditional as our conclusion. We just have C. So how do we get C? Well, C here is the consequent of a conditional. So we could get it by conditional elimination if we had the antecedent of the conditional. But we don't have the antecedent. But notice what the antecedent is. It's a conditional. So if we want to get a conditional, we use conditional introduction. We assume not A. We want B. We can get B by disjunction elimination of 2 and 3. And that proves that if not A, then B. That's conditional introduction 3 through 4. Okay. Now that we've got that, that's the antecedent of the conditional, we can get C by conditional elimination of 1 and 5. And that's it. C is our conclusion. Now, what this problem shows you is that you can use this conditional introduction anywhere in the derivation. It doesn't have to just be to get your conclusion. It can be to get any conditional. Like here, we needed this conditional to get our conclusion. So we can get this conditional by a conditional introduction, like we did here. Now, once we have this has been proven true. And so we can use it then just like any other sentence. And another important point, if you do a conditional introduction like this and you get not A conditional B and you do other stuff, once this subderivation is closed, it's closed. You cannot use any of these outside of this indentation. Okay? That's because, again, this was all based on an assumption, namely not A. We don't know if that's true. So the whole reason we indented was to quarantine this stuff away from the other proof, because we don't know if it's true or not. So once it's quarantined, it has to stay quarantined. Once you stop or close this subderivation, it's done. You cannot use it down here. You cannot refer to any steps in the subderivation after the subderivation is closed.